This next section is on conditional probability and the general multiplication rule. So in the previous section, we talked about and probabilities, and that was a multiplication rule that applies to two independent events. Now we're going to talk about a more general multiplication rule, which actually applies to both independent events and dependent events. Okay, and that involves a thing called conditional probability. So let's go ahead and start to talk about that. Definition: conditional probability. The notation P of F with the vertical bar down the center, E, is read the probability of event F given event E. So it's the probability that an event F occurs given that event E has already occurred. Okay. All right, so let's demonstrate this with the example here. So suppose a six-sided die is rolled. What's the probability that a die comes up 4? Now this is not a trick question. In a six-sided die, there's only one 4. So the probability of getting a 4 is, well, 1 out of the 6 sides. Right? Now suppose that the die is rolled a second time, but we're told that the outcome will be an even number. Okay, so we're told that the outcome is going to be an even number. What's the probability that the die comes up 4? Okay, so we're already given some information. Let's say, for example, I roll the die, I hide the result from you. I'll tell you, like, okay, well, it's an even number. Now you tell me what's the probability that it's a 4. Okay, so let's illustrate that with a Venn diagram here, where this is your sample space S, and the event of there being an even number is here, and we know that there's only 2, 4, and 6 that are even. Okay, everything else like 1, 3, 5 are just floating outside of that. Okay, now what we do here in this case is we essentially know that it's an even number. So the question is essentially, what's the probability that we get a 4 on the condition that we already know it's even? Okay. Well, we notice that instead of considering the entire sample space, 1, 2, 3, 4, 5, 6, we narrowed down our sample space to a smaller set. Okay, so a conditional probability always does is it narrows down your sample space, okay, of all the values that you're considering. Okay, now how many are both even and 4 in this case? Well, there's only one number that's both even and 4, and that is, well, 1 out of the 3 possibilities, right? Because there's only 3 that are even. Okay. Now I do want to cut this down the middle here. We can use some sort of formula for this. Okay. So the formula is the probability of F given E is equal to probability of E and F, their intersection, divided by the probability of E. So you'll notice that the denominator matches up with what we're conditioning on. Okay, we can also count the number of elements in each one of those sets too. So sometimes this is the preferred method right here. All right, so in our case, if we were to do the formula here, we have the probability of 4 on the condition that we're even. Well, we can do it actually both ways if we really want. It's the probability that we have 4 and even divided by the probability that we get an even number. Okay, so let's do the denominator first. What's the probability of getting an even number? Well, there's 3 even numbers out of the 6 possible, right? So we have 3 out of 6. That's a fraction downstairs. And then upstairs in the numerator, how many are both even and 6? So that's kind of its own, you can think of that as its own set, the 4. So the intersection of both even numbers and 4, well, there's just one number. Okay, so it's 1 out of the 6. Okay, and the idea here is that when we divide fractions, we just keep the fraction the same in the numerator and multiply by the reciprocal of the denominator. So the idea here is that the 6's cancel out, and we get 1/3. You could have also used the number of elements in each one of them. And that's essentially what we did in this case, in the first case. We just counted the number of elements that are both E and F. We said that that's 1, right? And the number of elements that are even, that's 3. So that's essentially what we did in the first case. All right, so let's continue on with this example. And for conditional probabilities, using tables is really nice. Okay, you'll see why. So we have this table of a group of adults that are divided into sex and then the hand they write with. All right, so either left-handed, right-handed, or male-female in this case. We can clearly see that the totals, columns, and rows are already calculated for us or created for us. We also see that there's a total of 100 participants in this survey. Okay. So the first question is, what is the probability of choosing a left-handed individual? Okay, now they didn't say anything about whether they're female or male, so we can just say probability of left is, well, how many people are left-handed? Well, there's 20 out of a total of 100. Okay, that is, if we divide those and make a decimal equivalent, that's exactly 0.2. B, what's the probability that randomly chosen male is left-handed? Okay, now it's a little subtle there, but this is actually a conditional probability. Let's read that again. What is the probability that a randomly chosen male is left-handed? Okay, something was given to us. Something, we were already told that something has already occurred, essentially. Okay, and they're telling us that what's the probability that a male is left-handed? So we already know that we're only considering those that are male. So if we just ignore everyone else, we're just considering the males here. That's a conditional problem. We narrow down the sample space. Instead of considering all 100, we're only focused on the 50 here. Okay, so the probability that this person is left-handed. So this is how you would write it. Probability of left-handed on the condition that we're dealing with the male. And we count the number of males, and we count the number of males that are both also left-handed. Okay, so I prefer this version of the formula instead of the probabilities, because then it's always going to be out of 100 and they're going to end up canceling out, so it doesn't really matter. All right, so how many males did we have? Well, I just circled it. It's 50. And how many are both male and left-handed? Okay, so if we're considering the left-handed folks, well, there's left-handed people here, right? And the intersection there is a 12. So there's 12 out of 52. Okay, now this is also going to terminate as a decimal. If you just multiply both by 2, numerator and denominator, you get 24 hundredths or 0.24. C, find the probability for a female to be right-handed. Again, it's a little subtle there, but this is a conditional probability, the way they ask it. We already know the person's female. We're conditioning it on that the person's female. So the question is, what's the probability that this female is right-handed? Right. Probability of right-handed on the condition that it's female. Well, again, the number of both right-handed and females, and the number of those who are female. Go ahead and erase the highlighted stuff here. All right, so let's highlight all the females here, and then let's highlight all the right-handed folks. And there's clearly an intersection there. Okay, we're conditioning on females. So the number of females is 50. Right, both those who are both right-handed and female, well, it's circled right there. It's 42. And again, you can multiply both numerator and denominator by 2. We get 84 out of 100, or 84 hundredths as a decimal. Okay. Now this next one, part D, is very similar to part C, but you'll notice something different. Find the probability that a right-handed person to be female. For a right-handed person to be female. All right, so we already know that the person is right-handed. All right, so we're conditioning on that this person is right-handed. So we say, what's the probability that we choose a female on the condition that they're right-handed. Okay, so it's just the opposite of part C. Again, we're counting the number of those who are female and right-handed. And then the denominator is the number of those who are right-handed. Now, the denominator here would be those who are right-handed. That's a total of 80. And those are female and right-handed. Well, it's the same as in part C, the intersection, which is 42. So you see it's a different probability altogether. It's 42 out of 80 instead of 42 out of 50. And if you put this into your calculator, you're going to get something like 0.525. Again, that will also terminate. All right. So I did mention about the multiplication rule for probabilities for a probability of event E and F only applies for independent events. Now, what happens when we have dependent events? Well, this probability of E and F is equal to the probability of E times the probability of F on the condition of E. Okay, that's if the events are actually dependent on each other. It also works if they're independent because conditional probabilities tend to reduce down to just the regular probabilities. So for example, probability of E on F. If E and F are independent, then if you can, even if you condition on F, it makes no difference. It's the same thing as just probability of E, right? Because they're independent. Probability of F on the condition of E, that's just probability of F. Okay. So that last factor in this formula here could just revert back to the multiplication rule for independent events. So let's see how this is actually done. And we kind of already did something similar to this. It's not that complicated. You'll see in this example that it's something that we've already kind of seen before. All right. When Rachel draws a card and she does not replace the card back in the deck, again, these are going to essentially tell us that they're dependent events. Let's say Rachel then draws a second card. So there's a subsequent draw from the deck after she's taken out a card, okay, and does not replace that card back in. All right, so for the first part it says, what's the probability of drawing a heart first and then a heart second? Okay, again, this is an and probability, and these are dependent events. So we have to use the general multiplication rule, and it goes like this: probability of a heart first and a heart second. Well, using the general rule from above, well, that's the same thing as saying the probability of a heart first times the probability of getting a heart second on the condition that we got a heart first. Okay, now that second factor here, it looks complicated, but it's actually a lot easier than you might think. We've already talked about this in some way before. Okay, in the first draw from the deck, the probability of getting a heart is, well, it's out of 52 cards, so there's 13 out of 52. Okay, that's 13 out of 52. This next one, the next probability is also another fraction, so this whole thing is just another fraction. But in this case, because the card was not replaced back into the deck, we do not have 52 cards. We have one less. We have 51. Okay. Now, what would be the probability of getting a second card if the first card was a heart? Well, that first card wasn't placed back into the deck, so we no longer have 13 hearts. We have now 12. Okay. Now we can do some reduction here. We know that 13 out of 52 is 1 and 4. We also know that 4 goes into 12 3 times. So this fraction is 3 51s, which actually can be reduced to 3 goes into 51, turns out 17 times. Okay. And the second one here, again, what is the probability of drawing a heart first and a diamond second? Again, it's one of these and probabilities. So it's going to follow this this formula here, because they are dependent events. So we're getting a heart first and a diamond second. Okay, so it'll be slightly different. There is the probability of getting a heart first times the probability of getting a diamond on the second draw, on the condition that the first one we know was a heart. Okay. Again, these are dependent events, so that second probability is affected by the first, right? That first fraction is, again, 13 out of 52 times, and then this other factor here is just another fraction. Again, we are not replacing that first card back into the deck. We have 51 cards. Now, as far as diamonds are concerned, the first card that we took out was a heart. Okay, we're given that the heart was already taken out. Now, diamonds, well, these were unaffected, right? They still have 13 diamonds in your deck. Okay, again, let's go ahead and divide this. This is 1 and 4. The 13 doesn't divide with the 4 or the 51, so we can just multiply straight across, and we get 13 out of 204. All right, that's it for this section.